talking in English, if that's okay, and maybe without a mic. Can you hear me in the back? Is it okay? Yeah? Well, if you can't hear me, just raise your hand and I'll take the mic. Also, I have changed the topic of this presentation, so if you're referring to the book you have in front of you, it's probably not going to be of much help. But as Simon said, you get two talks for the price of one. So this is going to be a talk about symmetry networks and three applications we made of them in cognitive modeling. So what happened is that we have been running repeatedly against this notion of symmetry network. And I'm going to explain a little bit, just very rapidly, what these are. By the way, this is going to be a talk with lots of images, lots of, well, maybe one video, no map. Let's keep it easy. It's early in the morning. And I will show a first application of symmetry networks to the topic of location-invariance in visual word recognition. Then we will switch to spoken word recognition with an application to time invariance. If I have time, I would like to talk about this application to generic object recognition with a trace rule. And maybe, my apologies for this, I think this is not the right format. Yes, if I have time, I would like to talk about another line of research that we have done recently with monkeys. Okay. So what is a symmetry network? Well, it's pretty much what you think it is. It's a network in which, well, the precise definition given by Shawe-Taylor in 1993 is basically a feedforward network in which you have some weights that are divided into equivalence classes. So basically, some weights are identical. And the way they are identical determines the properties of a network. So here, quite simply, you have a network that exhibits mirror symmetry. Because these weights, and well, this weight and this weight are identical, and the same here. So if you switch the inputs in a mirror fashion, of course the output of this network is going to remain the same. So you enforce some kind of symmetry in the network by carefully building it with equivalence classes of weights. All right. So a first application, well, our first encounter with this network was in the context of location invariance. Okay, so there's this, I mean, if you think about it, how we can actually represent words, access them, the sounds, their meaning, it's pretty amazing. I mean, we have something like, and that's a low estimate, I think, 70,000 words. We can access them in less than 300 milliseconds when we read them. And actually, right now it's kind of the operational way to distinguish between humans and machines. That's called the captcha type of way. Do you know these things? Probably you've been running into them if you're browsing the internet. So these are words that have been transformed. They have well, as you can see, they have a wave-like deformation thing. They are blurred, noise is injected into them, and when you present that to a machine, unless prohibitively vast computational resources are summoned, the machine is not going to be able to do it. So I'm not saying that it can't do it, but it's going to be very, very expensive. Whereas we can, I mean, is there anyone in this room that cannot read this thing? I don't think so. So what we did, by the way, and not only is it amazing that we can do that, given that we have so many words to remember, we do that extremely fast, and we still don't know how we do it, but however we do it, it has to be very, very fast. Because when you present such primes in a mass priming experiment to humans, so you're a subject, you come into the lab, get yourself in an experimental box, you have a screen in front of you, and then we ask the subjects, we tell them that some string of letter is going to appear on the screen. And please hit the right button if this is a word, and the left button if it's a non-word. And when we do that, with this word unique, they are faster to respond yes to this word when they have unconsciously been primed by this captcha for 15 milliseconds. So it's completely transparent to them. They are unaware that they have been primed by this captcha. But when they are primed, they are faster, I mean significantly faster at responding. So whatever happens here is very robust, very rapid.
So with that particular design, would you say that subjects would not be aware that they've seen a funny word before?
No, absolutely not. 50 milliseconds is sufficient to ensure that. Well, the mask before and the fact that the target happens just after the prime cuts the processing and prevents the subject from being aware of that. You can measure that by deep prime measures. But that's not the only demonstration of the flexibility and the robustness of this system. So there's the well-known, infamous Cambridge email that you might have received. It's an email in which all the words were scrambled, if the letters in the words were scrambled. It's talking about researchers at Cambridge University. Maybe you've received that. It was a viral thing at some point 3 years ago. And well, the important thing is that you can read these pretty naturally. I mean, you basically just run through the paragraph and there's no problem. So scrambling the letters doesn't make a big difference. Here, and this is what we call the transposition effect. So I don't know if you can see that here there's a transposition. Maybe some of you here didn't notice it immediately. So we wanted to know, so the question we asked was, what is it that makes this system so robust, for instance, to transpositions? And the hypothesis we had was that maybe this is just a byproduct of something that is much more parochial, much more trivial, which is location invariance. The fact that you need to be able, even though I think someone mentioned yesterday that when we look at words we foveate them, even granted that a saccade to a word is not precise. So even if you try to make sure that the word always falls at the center of your foveate, you're going to fail. And a few millimeters of imprecision make a big difference on the retina. So the pattern that is being imprinted on the retina when we read is always very different. So the system has to be able to recognize words at different locations. And we wanted to know whether it could be the case that, yes, the flexibility of this system is at least partly due to this need for invariant to location. So we took the simplest possible network we could think about. It's a network that has something like 1,200 words in its top layer, and inputs are represented here, and the input words are presented here in the input layer. And it has one hidden layer that does some computing that we don't know yet about. And when we train that using, the basic backpropagation, the question we asked was, do we get transposition priming? When we present when we train this network using location invariants, so if during training the word was presented at every possible location here, and we told the network that it was the same word as an output, do you get more transposition priming than when during training the word is always presented at the central location? And when you do that, well, you see that we get transposition priming in this circumstance. Transposition priming, by the way, is defined by the fact that you get more activation if you transpose two letters than if you substitute them altogether by completely different letters. So we get more activation when we transpose two letters in the input than when we substitute them altogether in this condition of training with different locations. But when we present words always centrally, this fails. So that was a nice demonstration, we thought, that location invariance might be involved in this robustness. But now we wanted to know how, and how does the network does it, you know? That's the problem with backpropagation networks, or I guess at every connectionist network. You end up with these hidden units, and you don't really know what they refer to, what they do. And to know that, you need to go into the network itself. You need to go deep into the plumbing. And this is what I'm going to try to do here. So let's start with the weights, the connection weights from the input to the hidden layers. So that's it. This is the whole connection weight matrix. One column here stands for all the connections that are being sent from one unit at one location to all the hidden units. So if you have 4 columns here, oh, wow, I have lots of animations that I'm not going to pass on this format. So this is going to be complicated. I think I'm going to switch to mine, actually. I'm sorry about that. So, where was I? Yes, so every column in this matrix is basically all the connections that a letter sends here, from sends to the hidden layer. So if you have 4 columns here, you have a word, and here you split the word time. Okay, now can you see something in this weight matrix? Yes? Periods. Yes, it is period. But there's something here. There's a symmetry. Well, you know, just look at the spots a little bit. These ones, for instance, they are all precisely at the same location. They fade a little bit from right to left, so it's not perfect. But there is something. You can quantify that just by looking at.
Wait, each group that you show is 260 units, or?
Yes. Yes.
Can you go back?
Sure.
I didn't quite catch that.
So you have 260 units.
Units. And so each column is the set of weights that go to the 91 units.
Yes. Each unit is a bank of 26 letters times 10.
Right. So I mean, the periodicity here is not really a periodicity. It's just a replication.
It's a replication.
Right.
It is. So the network, the backpropagation network, well, the backpropagation learning algorithm has found a way, well, the way it deals with the problem of location invariance is remarkably simple. It just replicate the weights.
Reinvents weight sharing.
Excuse me?
Reinvents weight sharing.
So that's yes, and now it's weight sharing, yes.
We share without we share.
Well, it finds it itself. So that's, I think it's so you can put a measure on that. You can look at how similar these weights that are coming from the same letter at different locations are from one another, compared to weights that come from different letters at different locations. And here you have the weights that come from the same letter at different locations. And as you can see, the standard deviation is very low compared to the weights that come from every possible location, which are much more flat in distribution. So the fact that the standard deviation is very low means that they are very similar to one another. So you can put a number on this translation symmetry, but it's not perfect, as you've seen. The patterns fade away a little bit. And in fact, what happens is that the patterns are very much alike when they come from contiguous positions, and they are more distant when the distance increases between locations. So the translation is not perfect; it's broken.
Well, that's just because the statistics of characters that begin and end typical words is different. So, I mean, you have, you know, in Italian, you have a lot more I's and O's and A's at the end of words rather than others. In French, you have more E's and S, depending on and T's.
Mm-hmm.
So the statistics are different at the end. So you're not going to get the same weight patterns just because of that. If you had, you know, if you had kind of a quasi-infinite input and then you took just a central part, then you'd probably be fairly.
So this is true, and you can do it in another way. You can induce a circular topology on the input. Just make sure that it goes around, and then you will assume that the broken symmetry will disappear. I think that's correct. We haven't done it. I think that's correct, but it's not the only reason why I think the network finds this way to break the symmetry. The thing is, if you have a perfect symmetry, you don't want that. For reasons that hopefully will become obvious in 1 or 2 slides. So imagine a network that has this weight property. You know, weights from the same letter at different locations are pretty much alike. Then when you present something, let's look at the activation patterns you get here, just by presenting different letters at different locations. Okay, and we collect all the activation patterns we get here, and just look at them. These are activation patterns in 91 dimensions, so you want a way to put them in 2 dimensions so that we can look at them. I'm using the standard multi-dimensional scaling thing. Again, can you see something? It's pretty clear that letters that have been seen at similar locations are grouped together. Okay, and this is more or less an obvious consequence of what we have seen with the weights. Of course, it's going to happen this way, because if you present letter T, just letter T at a certain location, you're bound to get one activation pattern that is going to be very similar to the one you will get if you presented T 2 locations away, for instance. Question? No?
Can I just check, when in the training, are you presenting time sequentially like this, or you just randomly choose a position? Is that right?
We are presenting them sequentially.
Is that important, do you think?
I don't think it is important for this network, because
it depends how you train it. Do you train with stochastic gradient or batch?
Batch.
Okay, so for batch it doesn't matter.
Yes, I don't think it matters for batch.
But for stochastic gradient it does matter. You don't want to do it sequentially, it doesn't work.
Okay, so why is that?
Well, because if
yes, yeah, of course.
Because the output doesn't
change the
change.
weights at every.
So just adjust the bias, the output bias, to get the right answer, and then it doesn't work.
Well, it will change. Have you done that?
Yeah. I mean, not with this problem, but it's a common mistake that I give to every student when I teach a class of machine learning. They don't scramble the samples, and it doesn't work because they always, they show example zeros and then all ones and then all twos. It doesn't work.
Okay, no, that's a good point. No, so we don't scramble the examples. So here we are with letter clusters, and now maybe some picture of how the network actually manages to recognize words independently of the locations is beginning to emerge. So what's the simplest hypothesis from here? Could it be, for instance, that the code you get for time is just more or less the code you get for T2 plus I3, M4, and E5, some kind of a slot coding thing, but distributed over the whole input units, hidden units. Well, if you test this, if you look at the sum of letters, just as I described, you compute activations, you compute vectors for every word in the training base according to this simple formula I just showed. And you compare the distances you get in this world between all the words. You compare these distances to the distances you have in the network for the same words. You get this huge correlation of 0.99. So it looks like this simple, very simple way to represent words just by the sum, basically, of the hidden patterns you get for the letters that make the word. If this is sufficient to explain what the network does, period. 0.99. But this, there's a little problem with that, isn't it? I mean, time, so that's okay with time, but let's look at another word, like a vial. A vial is an anagram for I don't know, veil, I think. So how does the network distinguish between those? You want to be able to distinguish between anagrams. In this training base, we had like 1,200 words. 400 of them were anagrams. So if the network really uses this kind of crazily simple thing, how does it manage to obtain 100% recognition? Something else is going on. And this is, I think, where the broken symmetry really kicks in. You don't want all the weights to be completely identical. You want some measure of distinction between locations. And you want to be able to distinguish very, very robustly between locations in these cases where you have anagrams. So here is a fourfold anagram: veil, vial, live, and evil. And I don't know if you can see the colors, but if you can, then it's pretty clear that, so this is an MDS again. This is all these words have activation patterns, and again, I have projected these words into, which live in an 81, I think, dimensional space, into a 2D space, so that we can see something. And they are neatly, friendly, aligned on a grid, and the dimensions of this grid are very clear. Here you have words, and then you have location. Right? So for anagrams, for words that are easily confused, you want to keep a measure of location in them. So the network departs from the simple linear equation that I showed before. It departs from this equation for these words, makes a special treatment for them. So this suggested that you still have a measure of location sensitivity in the system. So if you just take the activation patterns for these words and you more or less blindfold yourself, just by looking at the position, just by knowing the position of a word in these XY coordinates, you can more or less tell where it was presented. Just look at the x-axis and you're done. If the word you're looking at is there, it's around there in the map, then you know that it was presented in the right of the input layer. Okay, and is there any hope that this might be true in the brain? I mean, there's this well-known area that was discovered in something like 1999 or maybe 2000 by Cohen and Dandurand and people at the Collège de France. There's this area called the visual world form area, and it's in the left hemisphere. It's a very small thing, a few square millimeters, close to well, in the fusiform, at the frontier between the occipital and the temporal lobes. And this always lights up when you see something that looks like a word in your language. So if you hear a word, you hear me talking, saying a word. It doesn't light up. You see an image, it doesn't light up. You see a word in another language, like Chinese or something with other characters or another statistical distribution. It doesn't light up. It lights up only for words that you know, that looks like words that you could encounter. You know, this thing, the visual word form area, it's considering its location, it had long been thought that it will be completely location invariant because it's at the end of the ventral stream, basically. Where I think that Simon mentioned that yesterday. You don't want neurons at these regions to maintain any information about location. You just want the shape, the identity of the object, but you can discard information about location. And that was what we thought was going on with the visual word form area. But very recent results from Rauschecker at Stanford University show that this is not the case. Actually, they presented words to a subject in an fMRI setting, and they presented words to the subject at different locations. And then they blindfolded themselves. They took the activation patterns from the fMRI, and they put a linear classifier. Well, was it linear? I don't know. It was a classifier. And they put the classifier to work on these activation patterns. And here are the results. You get very, very good classification by location. So the classifier was able to tell very accurately, I think it was something like 70% accuracy on distinguishing between left and right positions in a word in the visual word form area. Of course, you can do it in V1, you know, but in the visual word form area, they still got something like 75%. And by the way, if they took the activation patterns from the white homologue of the visual word form area, the accuracy reached something like 89%. So there is something, there is information about location in these patterns. So the visual word form area, the thing that we're pretty sure is dealing with how to encode visual words, it is sensitive to location. Now, this is just to tell you that, well, maybe this rings a bell. It's a demonstration that words, well, the classifier makes more errors when it tries to classify things in 6 locations, when the things that it tries to classify are next to one another. So not only is it location sensitive, but it's retinotopic in a sense. Things that were presented close to one another, they elicit activation patterns that are close to one another.
But it's not geometrically retinotopic in the sense that
oh no,
the activation doesn't move within the area, right? It's more like it changes, but it doesn't actually move.
Okay, good point. I think it's true. Yeah, I think it's not. Actually, I have a visual about that. That's only one subject, though. Yes. So you can see in V1 and V2, you have this kind of, I would say, canonical retinotopy. But in the visual word form area, things are much more muddled. So the visual word form area actually cares about location. And this is something that our model does too. So I thought maybe we could do something with that. But that's the model again. hyped up. Yes, and we think that what is going on with this model is that it's mapping something that is location specific to something that is location invariant. By the way, Shawe-Taylor and colleagues, they put their classifier to work on the patterns of activation that were produced in Broca's area, and there the classifier was at chance. So in Broca, you don't get location sensitivity. No, you don't have that. So we think this is, to say it simply, we think this is Broca. We think this is some kind of region, like maybe VO here, that is location specific, we know that. And we think this is the visual world from area. Okay, this is the simplest interpretation we can have of what this model is doing. When we classify the patterns presented in the input layer, we already get this kind of course we get this kind of retinotopic distribution that Shawe-Taylor and colleagues observe. And when we look at how the classifier is, how well it is doing on the activation patterns in the network that were produced by rods at different locations, we get a pattern that is very similar to what they get. They have better accuracy in the middle because, well, and we don't, but because there's no notion of centrality in this network. There's no notion of Fovea. There's no eccentricity. There's no. I mean, it's really simplistic. So that's it. And now for predictions. What does this tell us? I mean, this model is making two very clear predictions. The first prediction it's making is that at the beginning, when the model is not trained, you should be very bad at recognizing words, but you're going to be very good at recognizing where the thing that you've just seen and couldn't recognize was presented. So you're enabled to tell that time was presented at location 2, but you can say that it was presented at location 2 in this network. So there's a trade-off between recognition and location specificity. So the untrained model is really bad at recognition, but it's good at location sensitivity, basically. And the trained model is the contrary. So the first prediction is that kids, you know, if we were to do exactly the same experiment with kids, we expect to find more location sensitivity in the visual world from area. The second prediction is that if the words are hard to distinguish from one another, as is the case for anagrams, the model, well, a classifier will have a better time at classifying those, because the visual world from area and the model have made it so that the patterns that correspond to these words that are very easily confused can be distinguished by making them much more location specific. So we predict that that if you did the same experiment as they did, but with anagram words, we predict that that you're going to be much better at location at classifying them by location.
Can you just say what 2 class and 6 class are?
Oh, sorry. Sure. So 2 big columns, untrained and trained model. In each column we have the recognition weights. 2 class is the accuracy of a classifier on 2 classes. It's just left or right. 6 classes is 6 locations. That's it. Good. So the summary for visual words is that, well, when you train the simplest, I mean, one of the simplest possible network you can think about to do word recognition independently of the location at which things were presented, what you end up with is a symmetry network, a broken one, a broken symmetry network. And this thing actually has some bearing on recent developments, you know, in the neuroscientific community. And the nice thing with this little network, the nice thing when you do really simple networks is that, one, you can understand what they do, and the second thing is that they make really clear-cut predictions. You just have to test now. Okay, I'm going to switch to the second topic here, and this is spoken word recognition. So we were very lucky because Jim Magnuson, who is a prominent researcher in the field of spoken word recognition, had the good idea to come in Marseille for his sabbatical. Spent 1 year here, and he was interested in just looking at the similitudes and the differences between spoken and visual word recognition. And he had another thing in mind, which was to take the most famous spoken word recognition model, which is called Trace. It was done something like 26 years ago by Ellman and McLennan. And he wanted to tweak it, or to upgrade it to a 2012 version, basically. So we assisted him. And here's Trace. So that's a model that is basically, uses all the principles of connectionism as defined early on by McLennan. And I mean very early on, not the strong, hard type of connectionism with learning distributed weights that we have just been discussing, but the earlier still connectionism type with units whose activation increases and decreases. You have time dynamics, you have no training, and it's a hierarchical process. So here, the input, the speech signal comes in, and it is analyzed in terms of features, which feed a phoneme level, which feeds a word level, okay? And the activation in all of these little units varies as a function of time and who votes for them. Basically, it's an election process. These things vote for things they belong to. A feature that belongs to a phoneme here is going, if it's activated, it activates it, and it's going to inhibit, well, no, not in this network. Things compete with one another here. There's this feedback. Basically, you can summarize the dynamics of this network as one of an election process with competition and feedback, basically. All right, but if you look at that, you see that what they had to assume for this network to work was that the whole lexicon, and it was a small lexicon, fortunately for them, it was 212 words, the whole lexicon has to be duplicated for every time slices you have in the network. So if your input uses something like 2 seconds of speech, they needed something like 200 time slices to represent these 2 seconds of speech. And the whole system here has to be duplicated at every time slices, so 200 times. It's enormously costly, and this is the reason why it has never been really scaled up. So what we wanted to do, and this is what I mean by this little TS and TS here. TS stands for time specific. It's just a way to label this strategy. They are using time specific units, and we want time invariant units. So we are okay to have a time specific phoneme level, where we duplicate every phoneme for as many time slices as we need, but we would like something that is much more economical, just to see whether it can be done. And we want a time invariant word level. We don't want to reduplicate the network every time slice. To do that, we need to introduce this intermediate level. That's the first difficulty. And the second thing is that we need a way to switch from a time-specific level to a time-invariant level. The reason why we're using this intermediate thing here is that it's really nice. It has nice properties. When you so the original trace thing had only phonemes that will fit into words. So basically your word is defined by its sequence of phonemes. We want another way to do it. What we want is, what we are using is a technique that is called string kernels, that is well known in the, I think, in the field of machine learning. It has many applications to computational biology, to automatic text processing. The idea is to represent sequences by the combinations of their parts, basically. Okay, so you have a sequence, a web page, for instance, a sequence of words, or you have a protein, or you have a brand of DNA, you know, and that's a sequence, and you want to represent it so that later on you can make some similarities between this sequence and another one in a very friendly way. You want to work in a space where these things have nice similarity properties, and you also want to be able to distinguish them from one another. You want this space to be linearly separable, if possible. One way to do that is to use string kernels. Basically, you represent these sequences by huge vectors. You know, vectors living in a huge number of dimensions, where every dimension stands for a possible combination of two entities in the sequence. This is what we do here. We represent words by a big vector, where a sparse one, where you get a 1, you put a 1 in a component if a letter combination is present in the sequence. So basically what I'm trying to say is that we have an intermediate diphone level where words are encoded by the combination of phonemes, the combination of two phonemes, rather than just a direct mapping. Yes?
So the two different things, and I'm not sure which one you're using. So one is the string kernel. The string kernel is really, you have n prototype strings, and then you have some measure of similarity between pairs of strings, and every string is represented by the vector of similarities of the input string to all the strings you already have, right? And that similarity, you can use it, you know, you can use the string kernel or something else.
Good.
And then you have something else, which is an n-gram representation, where you just have a big vector that represents the presence or absence of all successive combinations of 2 or 3 letters. So which of the two are you using?
That's, I think the second one you're referring to is the feature map. It's what is it?
Well, the technology people used to call these wiggle features.
Oh, so wiggle features the way they were introduced by Wiggle Green, I think, they need to be contiguous.
Yeah.
So we don't do that. But
oh,
yes. But we're using combinations of letters that can be distant in the sequence, and that will correspond to the second thing you mentioned. Okay. So now that we have our diphone level and we have our time-specific thing, we want a way to we want this model to be able to know, to be able to distinguish between AB seen at location 1, seen at time 1, and AB seen at, oh, let me do that again. We want this network to be able to recognize the same diphone at every possible times, and yet we want this network to be able to distinguish this diphone from its transposed version. Okay? If you get that, if you have a network that is able to distinguish between a diphone and its transposed, and yet if you have a network that can recognize every diphone independently of the time at which they're represented, then you have a win. Then you're done. So this is what, and this maybe rings a bell. This is what we've been doing all the way, all along with our visual words. So we tried to learn from that and to apply things we had learned with the symmetry network. And this is what we came up with. It's a little network. It's a symmetry network again. As you can see, weights are they are organized into equivalence classes. And here you have two symmetries. There's one anti-symmetry where the weights that come from one phoneme to a diphone decrease as the other, as the weights that come from the other phoneme at the opposite times increase. So that's an anti-symmetry. And then you have the mirror symmetry clearly between phonemes. Let's look into that. How does this work? You want this network to be able to recognize diphones whenever they were seen. Imagine A, B comes about in the speech. Okay, so we represent that by ones here. A1, B2 were activated. What is going to happen here? You're going to have these weights activated, and so the net input coming to AB is going to be 4. Okay? So now if you have A2, B3, as you can see, some other weights are going to be activated, but the end result is still going to be 4. Okay, so you always get 4 here. You can see that you always get 4 whenever the same diphone is being presented. Now, let's look at the other one. What you get here is 2. And if you shift it from one time position, you also get 2. So that's nice actually. You know, you can have a nice threshold and distinguish between these two activations very, very robustly. So this little symmetry network with a double strange symmetry, one anti-correlation and one mirror symmetry, does the job of activating the right diphones at the right time. All right, so now we're all set. We have this new system that doesn't replicate all the weights. It doesn't replicate all the units. It has only one time-specific level at the bottom, and then everything else is time-invariant. And when you look at you present all the words in the database to the trace model, and you look at the time at which these words are recognized. You do that for the trace model, and you do that for our new model, which we call TISC. And you correlate that. You see that the correlation is huge. I don't know why I don't have a correlation here. It's something like 0.8 something. So the correlation between the time taken to recognize things in the original network and in the new upgraded network is really good, you know, surprisingly good, considering all the changes we have made. And it doesn't end there. This is the kind of activations you get for different words that are related in some way. So they end with the same phonemes as in rhymes, or they start with the same phonemes as the target, as in cohorts. They are embedded in the target. You know, there are all kinds of possible ways to relate two words to one another. And the activation patterns you get for the target and the cohorts and the rhymes and the embeddings in trace look very similar to what we have in TISC. And then, of course, the whole point of that was to reduce the number, the computational resources needed. You know. So, for 200 words, the original lexicon, it's pretty clear that you're going to already have a huge cut in resources in TISC. When it gets to 20,000 words, it's really much better. And with a 70,000 word lexicon, the saving is now really starts to become you know, appreciated. All right, the prediction, the way we deal with recognition, with spoken word recognition, is to introduce this intermediate level that encodes the order between in the word by looking at combinations of phonemes. Because we look at the combination of phonemes, this way to represent order in a word is very robust to changes like transpositions. So we predict a transposition, a phoneme transposition effect in spoken word recognition. This is apparently, it's not my field, but apparently this is rather big. It's rather strange. It will come as some surprise. But there is very recent work that seems to support this claim. So imagine you have a change detection task. So you're a subject, and you're hearing the same word over and over again, and then suddenly, in the middle of the repetition, you get a word with a transposed phoneme. So for instance, you article, 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 and then in the transposition condition, you get article. And we ask the subject to press a button when they detected a change. Well, they are much faster at detecting a change when it's a double substitution than when it's a transposition of two phonemes. Okay? So apparently, there's experimental support for this notion that you might get a transposition effect. And trace won't do that. The original model won't do that. What it's going to do, if you present a word, so if you present the normal word, the normal target is going to get it. But if you present the word with a transposition effect, it's going to, the target is going to be dominated by a competitor. In our model, we don't get that. We still recognize the word when it is presented normally, but when the word is presented with a transposed phoneme, you get a huge confusion in our network between this word and, with transposed phonemes and the target, which could explain, which has a chance at least to explain what we observe experimentally. So my summary for spoken words is that we can avoid this whole real application strategy for words and phonemes with a symmetry network and a string kernel. And now, well, and we can reproduce some results from trace, but with less resources. And we have predictions again. Okay, how much time do I have left?
Un quart d'heure.
Un quart d'heure? Okay. Maybe I should skip this one. And directly get to the last part. So this is work we've been doing at the lab very recently with Dandurand Grainger. Okay, I'm getting back to visual words now, and this is basically, this was I just put that on the slides yesterday evening because I thought maybe you will enjoy that. So we're not going to talk about location invariance again. We're not going to talk about symmetry networks, but we're still going to be talking about visual word recognition in baboons and see how they do that. So let me show you, if I can, the video. It should work, but it doesn't work. Okay.
Maybe you should click into the key file. Maybe the link is broken.
Okay. I don't think it's going to work. All right. So, all right, that's not a big deal. This was just basically a video of the authors of the recent study that shows that you can indeed train monkeys to recognize words and to distinguish them from non-words. And in this video, you see how monkeys are trained. It's really nice. I mean, there's this. So monkeys are not. They are not taken into the lab to do the experiments. They don't have to sit there for ages, and we don't force them to do anything. You know, they are basically in what we call semi-freedom. They have a large open space in which they live, and at the bottom of this, at one edge of this space, 10 workstations, always open, and they can go into that, and there's always a screen waiting for them with some kind of stimulus. This is the experiment we're doing at the given time, and when they actually, so in this case, what happens is that when they enter into this little box, they have this screen, and there's a sequence of 4 letters. You know, it can be time, for instance, or it can be some kind of non-word, bleu. And if and they have a novel button and a triangle button, and if they hit the right button, they get orange juice or wheat, something like that. And they really love it. I mean, we have an infrared camera, and so we know when they come. Even in the night, what happens is that they wake up, they sneak in, and they do these things, and they get some orange juice, and they get back to sleep. So they really love it, and it's and when you use that, actually, you can. I think it makes a big difference on the cognitive tasks that you can have a monkey do when it does it by himself. It's different. So this is the paper by Jonathan showing that basically we had 6 baboons. Here's Dan, that's the star. He's like 308 words in his vocabulary. That was at the time. Now he has more now. And as you can see, as training progresses, they get better and better at distinguishing, at recognizing words. Now, that's kind of nice, but it's not really impressive if all they do is memorize patterns. You know, if all they do is memorize patterns, then yes, they can put 308 patterns in their brains. That's great. But they do something else. They do generalization. If you confront them to a new word that they have never seen, these are English words, by the way. You give them a new English word, and they will recognize it more accurately as a word. Well, in fact, what happens is that well, yes. Let me state it this way. So you have generalization in the sense that these monkeys they do not only make pattern recognition. They have extracted something from the language environment that they were exposed to, and we don't know what. It is true that the words that they were presented with had been carefully designed so that the letter frequencies were the same in the words and in the non-words. The letter location frequency was the same in the words and in the non-words. And the only thing that differed was the background frequency. So the idea, the claim in the paper was that they had picked up backgrounds. But how do you test that? Well, you test that again with a model, and now an even simpler model that doesn't even have hidden layers. Okay, so you just have inputs, outputs. That's it. It's a classification thing. And you want to test different alternatives, different hypotheses. What kind of codes did they use? They could be using something as stupid as the pixels. So we're cutting across a large literature showing that presumably we operate our decisions on more than pixels. But let's keep it simple. Imagine they just have pixels. Could they do the task? And could they generalize? And what if they used only what if they decided to encode words just by the letters, but not looking at the locations of the letters, but just is this letter present in the word? So representing words by sets of letters, not ordered sets, but sets. And then they could be using slot coding too. So leaf will be L1 plus E2 plus etc. Or they could be using a background code. All right. So we tested all of these little codes. We just basically generated one network for each of our monkeys. And you know, so this is a really simple model. It basically only has one parameter, which is the learning rate. So you have 4 codes, 6 monkeys, and the learning rate. So just by brute force parameter exploration, you can find the network that fits the data the best for every monkey. And this is what we've done here. This is what this confusogram is trying to tell you. And after parameter exploration, this is the fits we get. So this is the correct answers of the models compared with the monkeys as training progresses. And each of this panel represents a different code. Okay, so here you have, what's that? That's the, can't see it. Oh, thank you. Yes, that's a pixel, set, slot, and backgrounds. And as you can see, they all do pretty good, except for the set coding technique, which has a lot of trouble handling things like Hannagan, of course. Okay. Yes, and you can quantify the fact that backgrounds are doing a little bit better than the other ones, but that's not really clear. You know? We need something more serious to say that. So how about testing the monkeys again on something else? For instance, the transpose letter thing. Imagine after training, after the 6 monkeys have been trained, imagine you present them with words with a transposed words they know, but with a transposed with 2 transposed letters in them. So they ought to be responding that it's a non-word if they are to do the task correctly. You know, you take a word, you transpose 2 letters, it's not a word anymore. We make sure that it's not, and they ought to be responding non-word. But when you do that, they fail more often. More often than not, they say, it's a word. They do that more often than when the transformation you do is a double substitution. By definition, it's a transpose letter effect. So you get that with monkeys. Monkeys, not only do they learn, not only do they generalize, but they show a transpose letter effect. And our models, when we did the same with our models, the only code that could do it was the background one, for more or less obvious reasons. So the monkeys fail more often on TL non-words than on DS non-words. And the only code that does it is the background. So if you grant me that monkeys use a linear perceptron thing, very simple linear classifier, then this is evidence that they use background coding.
So I won't mind that ever.
No. Okay, why?
I mean, you asked if you grant.
Yeah.
I don't think I'd grant that.
Why?
Well, you know, because of the picture that Simon showed yesterday of architecture of the visual cortex that has, you know, 5-6 layers all the way up to IT. So it's just not a linear perceptron. Or if it's a linear perceptron, it's on features that are considerably more sophisticated than backgrounds. And
well, the fact that there's a hierarchy of layers is encapsulated in this model. The input changes. The input is supposed to represent things that are higher and higher as the code changes. So in the pixel code, we are assuming that the input is really, really low in the hierarchy. With the background code, we are assuming that what the system takes as an input is very high in the hierarchy.
I would have said that if you've already bought the idea that the input to the learning layer are bigrams, I mean, you've already done a lot of stuff already.
Yes.
There's lots of non-linear stuff to get to that stage, and you just say, would a linear classifier work, and it looks like it's doing a reasonable job.
I would agree, yes.
Well, so what you're saying is, you know, you have, I don't know, 7-8 layers, and you decide to name the last layer the classifier.
Yes. Yes.
But it doesn't matter. I mean, you can put the boundary any way you want. You know, you can say, well, the first 2 layers are the features, and then the rest is the classifier.
Yes. I would agree with that.
So in a sense, you don't actually have to make that hypothesis.
Oh, okay, I see what you mean. Okay, well, that's good news. Okay. Yes, well, it's good news and bad news. The bad news is that it's always the same thing with connectionist networks. You don't really know what these things, how to deal with a representational gap. We have these connections and units, and what do they really represent in the brain? So in the former, in the first part of this presentation, we could more or less get a mapping between every part of the system and this brain system that we were modeling. We could label the inputs, we could label the output as being broker, and we thought the hidden layer was the visual world from Maria. Here it's more, it's unclear to me. Yeah. And I think it's a trouble with connectionist models that ought to be addressed. There has been work in this direction, but not enough.
Do you think there's any reason to, I mean, I would say the bigram idea is actually more plausible than the idea that the monkeys have actually made explicit things about letters. I mean, I'd even say you might try the really dumb thing of just taking the whole lot and just learning every single word, the 308 words, as a different pattern, and then you just sort of say, okay, if the total amount of sub-threshold activity in my 308 word units is above a certain thing, I'll say, oh, it might be a bit. In other words, that's quadrams, if you like, and that would be that would be for me even the most stupid thing that the monkey could be doing. I mean, I don't see any evidence actually that they're doing letters at all.
Okay.
Well, they're generalized, right? I mean, you said that.
They do generalize, and it's how would you get generalization in a quadrogram setting?
Well, you'd have your 308. I mean, if you're talking about Dan, he's got 308 things that he recognises, right? And you can get those right. He's getting 90% correct. So, let's suppose that for each of those, when it's not the right word, it's not 0. It's some fraction of the total, the maximum activation, and you just sum up over all the 308 units, and you say, I'm going to guess that this is a bit like a word.
Okay. So yes. So you're assuming that. All right. So you want to look at the activation patterns across the whole lexicon of Dan, and make a decision based on that. Okay.
It doesn't have to be that, but I mean, in a sense, that's the dumbest thing that you could do. I mean, bigrams seem to be a little bit sort of. It might be true. It's better than pixels, and it's better than sets, and it's better than slots. But since you deliberately made the set and the slot data totally unusable because they're all equal between words and non-words, then it's not going to learn that by definition.
Well, actually, it nicely fits into the literature, some of the literature on this topic. So, for instance, people like Dandurand would say that they would say precisely that on top of this bigram thing, you have a quadrogram. I think he explicitly makes this hypothesis that you have a quadrogram level, or maybe some. Well, it's going to depend on the statistics of your language, or is it useful for you to represent things as quadrograms or not, or words?
People used to try and teach kids to read with the global method. It didn't work very well, but I mean. There's nothing in the way you train the monkeys to say that you're not actually doing global, teaching global reading techniques rather than actually looking at the letters.
Well, the generalization is what suggests that they don't, because they can figure out if a new word they've never seen before is actually an English word or not. So that is an argument against explicit templates.
I think it is, but I think Simon has also a point that you could still have some residual activation in the other words that could help you make a decision, even if you had only quadrograms. But it should be demonstrated.
Yeah, you could try it. Couldn't you? It wouldn't be complicated.
Yeah. Go ahead. So I guess that's the conclusion. Yeah, I was talking about symmetry networks in the beginning, and I think they can help us understand some aspects of language and learning. We had a broken translation symmetry for visual words that gives order to them. We have a symmetry network for diphones that can achieve the transition between a time-specific level and a time-invariant level, resulting in huge costs in computational resources. I couldn't present that, the trace rule. And then there is the boom study that I just mentioned. And a recurrent theme in many of his work is to use feature combinations to represent order in a structure. I think I will end there. Yeah. Thank you.
So that's explained by sort of complex cell type models, so clean models, where you have detectors that are essentially shift-invariant. I mean, that are not shift-invariant, but that are replicated across the visual field. And then you have local tools that say
HMAX, basically.
I call them convolutional nets or neocognition, but you know, HMAX came much later. They reinvented the wheel, basically. But I mean, it's basically Hugon with all 1962. Right? That's really where it comes from. And so you do some pooling. And if you have a pooling area, the output of the pooling area is like a histogram. It doesn't tell you where the individual components came from. You forget that information. And so if you think about sort of low-level feature detectors, when you pool, you get a little bit of distortion invariance. If you have individual letter detectors, when you pool, what you get are you have a bag of letters, and you don't know which order the letters come. And that would directly explain the transposition effect. And we even know what the size of those pools are. They're measured by visual prodding experiments by Dennis Pelly and others.
But wait, if you pool on letters at different locations and you lose information about the location, you end up with a set coding thing, which, is going to give you the transposition, but it's not going to give you recognition of anagrams.
No, but wait, it's local. It's local. It's not over the entire image. It's just over the size of a couple of characters.
Okay.
So the thing is, we even know, we can even measure the size of those pools. We know exactly what size they are.
I think I see what you mean.
And this was done by, among others, by Dennis Pelly in visual prodding experiments, right? So you show a character, you ask someone to fixate at a particular point, and then you show a character on the side. And then you ask the person, can you recognize the character? And for most cleanly written printed characters, you can recognize them pretty much anywhere they are. But now you put two flankers on each side or above and below, and then you bring them closer, or from above and below. And then there's a point at which you can't recognize this character anymore because the features from the other characters mix up with the feature of this one's in the same pooling area.
Right.
And you can identify exactly the size of that pooling area. And it's the minimum size of the pooling area that you have at that location. And the size of that pooling area grows geometrically with eccentricity. So what it means is that in the center of your visual field, you can do identification and localization. The pooling areas, the minimum pooling areas are very small, so you can distinguish a lot of things without shift invariance. But then far outside of the center of the visual field, everything gets confused. And so that explains why there is a limit to how many characters you can recognize at a time, right? So if you fixate a character at a particular location in the word, there's about 3 or 4 or 5 characters you can see at once. But further than that, you can't because the characters blend together. You can't make them out because of those pooling areas get too big and they mix multiple characters together.
Yes, yeah. I'm aware of the work of Dennis Pelly, but not as much as I should maybe. But I think the way he thinks about pooling and receptive fields and his crawling experiments is he has an underlying I think quantitative theory behind that, feature integration.
Yeah, it's pooling. It's the same thing.
So
he also changed the names instead.
And it's reminiscent of many of the things we do in the IA model, but it's much more sophisticated in the visual aspect of it. It's right. I think it uses the same mechanisms, but we should take that and integrate it in the inputs of our model. This is as you have seen, the inputs of our model are always very brutal, you know.
Well, basically, I mean, it's very simple. Instead of just having one hidden layer, so in your first model that you showed, instead of having just one hidden layer that encodes the, you know, the entire input, you basically just have a two-layer model. One which is sort of vaguely retinotopic, if you want, and then the other one has local pooling. It's basically the first two layers of a convolutional net. In this case, it would be a temporal convolutional net, and you wouldn't have weight sharing because, you know, it would be learned spontaneously. But you'd see this effect of transposition and
okay, so what you're saying is that we could dispense with any kind of so simply by this pooling mechanism that is local pooling, overlapping, I suspect.
Yeah.
You will get these combinations that will be unordered.
Right.
And this will give you both transpose data effects and recognition without invoking explicitly anything like a bigram or a quadrigram level.
Right.
Okay, no.
Right.
Okay.
So there's more recent work by Emerson and Shelley. I think it was, I can't remember where it was published, but maybe Nature Neuroscience. And they call them metamers. So they build a model, you know, very much like convolutional nets, with but the filters are just built by hand. So they have oriented filters, nonlinearity and pooling, complex cells essentially, and then the second layer of that, the second stage of that,
They train it, sorry.
No, they don't train it. It's just built by hand. It's basically wavelets and multi-scale. And then they do an experiment with subjects where they ask them to fixate the center of an image, and they scramble the periphery of the image in such a way that, for the point of view of their model, it makes no difference to the output. And it turns out humans are also insensitive to those changes. So you can't tell. So you build this model and you generate an input that will produce the same output representation as the original clean image from the point of view of the model. You can do this by gradient descent in input space. And then you show that image to a human. A human can't tell the difference with the original image, which means that the kind of invariants that are present in the visual cortex are similar to the ones that are. And it's very much like a transposition effect, except it's not on letters, it's on, you know, motifs in a natural image.
No, that's really nice.
Very recent.
Yeah,
it's just a few months ago. It's based on Dennis Kelly's work on convolutional nets and stuff.
Sounds good. Well, then again, you have to compare models. I mean, if, you know, you can exhibit one model that does it. It's evidence. It's not conclusive. If other models can also do it, and they may do it with less hypothesis. But I find that it's something that is lacking in this work. As I know it, he doesn't compare things.
Yes, I think we have to make a break and the coffee.